So 3.3 measures of variation. The key concept of variation is discussed in this section. It says it's the single most important topic in statistics. So this would be a section worth reading out of your textbook, maybe even more than once, because this concept, it says, is the single most important topic in statistics. So must be pretty important. This section presents three important measures of variation: the range, the standard deviation, and the variance. Standard deviation is probably the most important aspect of all of statistics. Okay. Here's a study hint. Part 1 of this section presents basic concepts of variation, and Part 2 presents additional concepts related to the standard deviation. Although both parts contain several formulas for computation, do not spend too much time memorizing the formulas and doing arithmetic calculations. Instead, make it a priority to understand and interpret the values of standard deviation. So, I'm not going to lie to you. As data sets get larger and larger, meaning bigger than 5 or even bigger than 10, as the data set gets larger and larger, the way that you find the standard deviation, the variance, is very time consuming. There's two different formulas. One is called a shortcut method, but it still takes a long time to compute. There is a lot of room for error when you're calculating the standard deviation of the variance. Not so much the range. The range is the easiest topic that we go over, or concept. It's the standard deviation and the variance that usually give students troubles, because we may have 30 data values, and if I find the variation of that using the shortcut method, probably going to take me about 45 minutes, unless the data values are really small. If I have 5 or 10 values, it may take me about 10-15 minutes. Okay, just really depends on the data set, and that means there's a lot of room for error, a lot of user error, meaning my error, because if I push one number wrong in the calculator, it's going to get off. So don't concentrate so much on the actual numerical answers in this section. Believe me, you'll get enough practice on the homework or on examples that we do in class. But understand what the variation is and what the standard deviation is. That's the main thing. And no, I didn't just say it's not important how you get the answer. It's important what the answer means. It is important how you get the answer. Just know that if you make a mistake working a problem for standard deviation, then you're just like everybody else in this class, including me. I've made several mistakes. When you do it out by hand, there's a lot of room for error because of all the numbers. Okay. Let's read this through this example real quick. It just looks interesting because I see big numbers. All right. The time unit of 1 second is defined to be the duration of 9,192,631,770 periods of the radiation corresponded to the transition between two hyperfine levels of the ground state of the cesium-133 atom. That's how 1 second can be defined. The definition redefines time, or that definition redefines time to be based on the behavior of atoms instead of the Earth's motion. It results in an accuracy of plus or minus 1 second in 10 million years, which is the most accurate measurement we use. Because it is so accurate, the second is being used to define other quantities, such as the meter. The meter was once defined as 1/10,000,000th of the distance along the surface of the Earth between the North Pole and equator, passing through Paris. The meter is now defined as the length of the distance traveled by light in a vacuum during a time interval of 1/299,792,458th of a second. When dealing with time measurements or time measurement devices, the traditional standard deviation has been found to be poor because of a trend in which the mean changes over time. Instead, other special measurements of variation are used, such as Allen variance, total variance, and TOH. Unrelated to statistics, but nonetheless interesting, is the fact that ads for watching usually show a watch with a time close to 10:10. That time allows the brand name to be visible, and it creates a subliminal image of a happy face. The time 1010 has been the industry standard since the 1940s. Kind of interesting. Is that really related to statistics that much? No, but it's still very interesting. Another interesting fact that I have recently read about, everybody knows about, if you're in here, you probably at one time or another, you've heard about the transcendental term pi. Pi is used to calculate volume of a circle, maybe of spheres, volume of a sphere, area of circles, circumferences of a circle, things like that. And it is a number that never repeats. The decimal never repeats. I usually only remember it out to 5 decimal places. But there are some people, I recently read about a person who calculated pi to 100 billion places with his computer. And it took him from, I believe it was July to December on his computer to calculate those places. We only need pi, this is a very interesting fact also, we only need pi to about 39 places if we want to estimate the volume of the universe to the nearest atom. So if you have pi to 39 places and you were able to use that to find the volume of the universe, it would be accurate to the nearest atom. If everyone in here hopefully knows what an atom is and how small that is, that just blows my mind. Anyway, if you don't understand anything what I just said, don't worry because you won't be tested on it. All right. Now, the first type of measure of variation is the range, and it's one of the easiest to calculate. You can see the range is the maximum data value minus the minimum data value. This is the range. Maximum data value minus the minimum data value. All right, so basically it's one number minus another number. Okay? It is then very, very sensitive to what? Outliers. Okay, just like the mid-range. Ooh, those seem kind of related. Mid-range or range. So say you got that same set of 10 tests. You know, you make a 20 on one, you make a 99 on one, then your range is very big, right? So, or big in a relative sense to tests. So that outlier of that one bad grade affects your range a lot. You would want a smaller range, I would think, if you were doing good in the class, because that would mean that your lowest test and highest test wouldn't have very much difference. Round off rule for measures of variation. That's the range, the standard deviation, and variance. We're going to cover those two next. When rounding the value of a measure of variation, carry one more decimal place than is present in the original set of data. So we have the same round off rule for measures of variation as we do the mean, the median, and the mid-range. Okay.
What is that? Carry one more decimal place?
One more decimal place than the original set of data is the round off rule. So how do we find the range again? You see right here we have 4 data items, chocolate chips. Take the largest data item, 26, subtract the smallest data item, 22, and you get a range of 4.0. Okay. Standard deviation is a very important measure of variation. I'd be willing to bet it's probably one of the most important terms that we've went over in this class so far. Your book says that standard deviation is a measure of variation most commonly used in statistics. So that must mean that it's pretty important. We have 2 formulas listed here for sample standard deviation. All right, and you can see these formulas are pretty involved. X is the actual data item. X bar is a mean. Of course, we all know what square means. The sum means you sum up each. And then in the denominator, we have n minus 1. So, and then after you do all of that, then you take the square root of it. Well, that is what some consider to be the long formula. Even though this formula looks a little more complicated, this is what's called the shortcut formula for sample standard deviation. I usually do all of my standard deviation using this shortcut formula. So what we have to do to be able to find the sample standard deviation is you have to know how many data items you have. That's your n in the problem. You need to make one column that's your x values, and then we need to make another column that's x squared values, and we need to sum up each column. And so if we take the sum of the column of the x squareds, it goes in right here. If you take the sum of the x values, it goes right here in your formula. And then ever how many data items you have, you'll say that times that minus 1 in the denominator. Take the square root of all of that, and you get your standard deviation. So let's look at a couple of important properties of standard deviation and talk about what actually standard deviation is before we work out a problem or two. Your book says that standard deviation is a measure of how much data values deviate away from the mean. The value of the standard deviation is usually positive. It is 0 only when all the data items are the same number. It is never negative. Right? Also, larger values of S indicate greater amounts of variation. If you have a small standard deviation, then all of your data items are probably pretty close together, meaning like the numerical value. If you have a large standard deviation, then they're probably spread out a little more. The value of the standard deviation S can increase dramatically with the inclusion of one or more outliers. The units of the standard deviation S, such as minutes, feet, pounds, and so on, are the same units as the original data values. It says the sample standard deviation S is a biased estimator of the population standard deviation S. Okay. We want to round the standard deviation to one more place than the original set of data. Okay. So here's a really, really small example on calculated standard deviation. Remember we had the chapter problem about the chocolate chips and the different cookies. And so if we had these 4 data items, 22, 22, 26, 24, we could find the sample standard deviation by using either of the formulas that we went over. Your book here is going to use the formula with x bar, with the mean. So it says the first thing you need to do is find the mean. Okay, so that's what they're doing here. They found the mean to be 23.5. Then they're going to take each data item, 22, 22, 26, 24, and they're going to say the data item minus the mean. And they do that for all 4 values. All right. Then they square each of those. So that makes, negative 1.5 squared becomes 2.25, and so on and so forth. Then they add all those together. Once they add all those together, they have that sigma x minus x bar all squared in the first formula we covered. I'll show it to you again. And this one right here, they have that. Then n minus 1 in the denominator is going to be 4 minus 1 because there were 4 data items. All right. 4 minus 1 is 3. They divided, and they got this here. And then you take the square root of that, and you get the standard deviation. And so since we had whole numbers in these data items, they took it to one place. So S, the sample standard deviation, is 1.9. Okay, so that's one way you could find the standard deviation of that data set. The next example of your book, and I'm going to work out some examples, so don't worry, I just want to kind of read through these first. The next example of your book works the standard deviation the way that I usually work the problems if I'm working them out by hand, because there are several calculators and shortcuts that will do this for you. Alright, so figure out how many values there are. There are 4. Then add all the values together. That gives you your sigma x. In this problem it's 94. Then you need to figure out the value if you square each data item. Okay, so they squared all the data items here, and then they added them together. That's your sigma x squared. Then in your formula, your sigma x squared goes here, n is on the outside, minus your sigma x, and this square right here is supposed to be on the outside of that parentheses. It's just a problem with the formatting in the textbook. So the square right here should be on the outside of the parentheses. Alright, and that's all over n times n minus 1. N on this problem was 4. N minus 1 would be 3. They worked it all out. They took the square root and they got 1.9. Okay, so, and I believe that's supposed to be chips, not chops. So that's 2 different ways to work that, that problem out. Now, those are really small problems, and you see just how many numbers there were. So if you start dealing with larger numbers, larger data sets, working out the standard deviation by hand can definitely be a challenge. Okay, and so I'm going to show you that in one of the examples I'm about to work. I'm going to go to the back of the section here. Definitely need a reliable calculator whenever you're working these out, because there's a lot of room for error if you have large data sets or large numbers. And I'm going to show you that. Alright, I'm going to work number 6. The top 10 most expensive colleges. Listed below are the annual tuition amounts of the 10 most expensive colleges in the United States for a recent year. The colleges listed in order are Sarah Lawrence, NYU, George Washington Bates, Skidmore, Johns Hopkins, Georgetown, Connecticut College, Harvey Mudd, and Vassar. Can this top 10 tell us anything about the standard deviation of the population of all U.S. college tuitions? Well, I can go ahead and answer that question. It can't tell us anything about the population of all U.S. college tuitions, because this is the top 10. This is the most expensive. We can't compare the data that we get here to the data of every college in the United States. Alright, so here are the tuitions listed. That's 10 data items. So what I'm going to do is I'm going to make a column. I prefer to do this kind of in a table and keep everything as neat as possible if I'm working these out by hand. Alright, so I'm going to make a table of all of my x values. These are all these tuitions that are listed. Okay. So I'm going to write these down. And I'll try to keep everything as neat as possible. It's so easy to get off one number and mess up your final answer. It's important that you're very careful, and you actually may want to go back and check some of your values as you when you finish writing them down, just to make sure that everything is correct. Almost got them all on one page. Not quite. Okay, so that's the 10 values. That's my data items. Okay, so I've listed all the x values. Now I'm going to make another column. It's going to be x squared values. So I actually have to take and square 54,410. So you can see that's a really big number. That's 2,960,448 and 100. 448,100. So billions, millions, hundred thousands, and then hundreds. So you can see why on a problem like this, one could very easily make a mistake. I've already worked all of these out, so I'm going to just write them in. Might take about a minute. Alright, so I have my x values in a column, and then I have the square of those in a column. Now, to use that formula, the second formula, I need to find the sum of x, and I need to find the sum of x squared. Alright, the sum of x is 515,966. The sum of x squared is 26,631,884,700. All right, and my formula for sample standard deviation is the square root of n times the sum of x squared minus the sum of x squared over n times n minus 1. N minus 1. Okay. So that's the formula I'm going to plug these into. These are very large numbers, so if your calculator does not hold a lot of places, you might want to maybe use the Windows calculator or an online calculator when dealing with large numbers like this. Alright, so the number of data items was 10, so it's 10 times 10 minus 1, or 9. Okay. Whenever you work that out, you're going to get a long decimal, and since you're rounding to one place because the original data set has no decimal, I would suggest carrying it out a couple places. When I worked that part out, this is what I got, and I went ahead and carried it out 3 decimal places, so I would at least do that. Okay, and then when I did that in my calculator, I got 1043.146117. Alright, and we want to round that to one place. So our standard deviation for this set of data is equal to $1,043.10. And I put, you don't have to put that zeros, just so you'll know that is cents, because it carries that same unit. Usually we write 10 for cents instead of just 1, but that is money. There is also another measure of variation that you can get from this, and it is the variance. And the variance is the sample standard deviation squared. So I would never, if I just worked the problem out, I would never just take the standard deviation and square it because of rounding problems. I would come over here and look what you were taking the square root of, this right here. That's what I would use. I wouldn't just square that. Never plug in rounded values into any type of formula if you can help it. So the variance on this problem is 1,088,153.8. Okay. So what does this standard deviation tell me? It tells me that this is the amount that my data items, my tuitions, this is the amount that they will vary about the mean of the tuitions. Okay, and so since this number, in terms of these tuition amounts, this number is pretty small compared to the amounts that we're looking at. So that means that they only vary about, $1,043.10 about the mean. Okay. Now, one like that, I mean, that's just, it leaves so much room for error that you have to be careful in working it out by hand. I'm going to work out one more, just one that's a little more manageable. Okay. I'm going to work out problem number 10. All right. Florida manatee deaths. Listed below are the numbers of manatee deaths caused each year by collisions with watercraft. Manatees, also called sea cows, are large mammals that live underwater, often in or near waterways. The data are listed in order for each year of the past decade, so 10 data items. The data are from the Florida Fish and Wildlife Conservation Commission. What important feature of the data is not revealed through the different measurements of variation? All right, so let's work on this standard deviation. Again, this is problem number 10. So I'm going to do just like last time, and I'll go ahead and start on the new page here. I'm going to do just like last time, and I'm going to make one column of x values, and then right beside it I'll make a column of x squared values. All right, so 78, 81, 95, 73, 69, 79, 92, 73, 90, 97. All right, beside that I'm going to square each one. And I've already done these, so I'll just write them in. Okay. So after you have all of your data items, all your x values and your column of x squared values, then you want to figure out the sum of the x column and the sum of the x squared column. All right, the sum of the x column, or all of my data items on this problem, is 827. The sum of x squared is 69,303. And we did say that n was equal to 10. Okay? So my sample standard deviation is going to be the square root of 10 times, remember this first value here, that's your sum of x squared. So that's 69303 minus the second number here is the sum of x, and we have to square it. That's all over the number of data items times n minus 1. So again, for us, it's 10 times 9. All right, if you work that out in a calculator, you should get 9101 divided by 90, or the square root of 101.1222 repeating. All right, if you take the square root of that and you round it to one place, you get 10.1. So your sample standard deviation is 10.1. Your variance is s squared. Your variance is equal to what you would have before you take the square root. So it's 101.1 if you round to one place. If we do have the standard deviation and we want to know if a data item, some item, would be unusual or would it be usual for the set of data, then we use something called the range rule of thumb. All right, so to be able to figure out this range rule of thumb, we have to have the mean of the set of data and we have to have the standard deviation. But what it allows us to do is figure out a range of usual values, and so then we could tell if we got a data item, another data item, we could tell if it was usual or unusual. All right, and the range rule of thumb, the formula is for the minimum usual value, and this is written out in words, but it's x bar minus 2 times the standard deviation. And the maximum usual value is equal to x bar, the mean, plus 2 times the standard deviation. Okay, so I'm going to look at these deaths of these manatees, the same problem that we were looking at. Let's figure out what x bar would be, or the mean would be, for that set of data. So add all the data items together, and you get, we already know what we get. We figured out that the sum of all the data items was 827. So take that, divide by 10, and you get 82.7. All right. We figured out that the standard deviation was equal to 10.1. So we can figure out the minimum and maximum usual values for a set of data. And that set of data was the number of manatee deaths in a year caused by, I believe it was collision with some type of water vehicle. All right, so the minimum usual value is going to be equal to 82.7 minus 2 times the standard deviation, and the maximum usual value is equal to 82.7 plus 2 times the standard deviation. All right, so let's see what we get here. So the minimum usual value, 62.5. Maximum usual value, 82.7. is 102.9. All right, well, it's kind of hard to have 62.5 Manatee or 102.9 Manatee. So you would want to just say about 63 and and about 103. So anything at or between those two numbers should be usual. So if you wanted to look at your set of data and pick a random year, say one year there were 69 and you wanted to know, is that usual? As long as 69 is at or between 63 and 103, then it's usual. But what if one of my data items was 110? Well, that falls out of this range, so that means that that would have been an unusual year, because that's an unusual value of deaths. So mean minus 2 times the standard deviation. That is how you find the usual values of a set of data. And then, of course, you can figure out the unusual from that. You can roughly estimate, and I do emphasize roughly estimate the standard deviation for a set of data by saying that the standard deviation is about the range divided by 4. So again, that's a rough estimation. So how would I do that with my other set of data? Well, I had to figure out the range. So look at the smallest year, that was 69. The largest year was 97. Is that right? I believe so. Sure, right? So standard deviation, if you approximate it that way, 97 minus 69 divided by 4. That's about 7, or is 7. So how close is that to the actual? I mean, it's kind of close. It's not like I got 10 here and I got 1 here. I mean, that is, 7 is close to 10. So again, it's a rough estimate. All right, population standard deviation. The only difference is, instead of dividing by the n minus 1, we have just n. That would be the total population. Okay? Most of the time we don't calculate population standard deviation. It's given to us. But population standard deviation, the symbol that we use is a lowercase sigma. And we do use population standard deviation a lot. We just rarely calculate the population standard deviation. It's usually given. Okay? All right, I told you earlier that variance was something else that we could calculate easily if we find the standard deviation. The variance is a set of values is a measure of variation equal to the square of the standard deviation. So a sample variance would be s squared. Population variance, again, there's another typo in this book. That should be sigma squared. All right, there it is. Population variance, sigma squared. Also, articles in professional journals sometimes are often used capital SD for standard deviation and VAR for variance. So what's important about variance? All right, let's read about variance real quick, see what the textbook says. The units of the variance are the squares of the units of the original data. All right, so if your original data was in feet, it would be feet squared. If original data is in meters, it would be meters squared. The value of the variance can increase dramatically with the inclusion of one or more outliers, just like the standard deviation. The value of the variance is usually positive. It is 0 only when all the data items are the same number. It is never negative. The variance, the sample variance, S squared, is an unbiased estimator of the population variance, S squared. And that population variance, again, that needs to be a sigma. Okay. All right, so I'm going to show you real quick, and you can. I'm sure you've read through the rest of this. I'm not just going to sit here and read the whole time. But look at this empirical rule right here. This is, whenever I first started learning about statistics, and I learned about standard deviation, I was good at math, so calculating the standard deviation wasn't a problem. But why would we want the standard deviation? If we have the set of data, then 68% of all the values will fall within one standard deviation of the mean of the set of data. 95% will fall within 2 standard deviations of the mean. 99.7% will fall within 3 standard deviations of the mean. All right, so let's look at that. If we were looking at a bell curve and we had our mean right here in the middle, this is the average, or I'm sorry, the mean, arithmetic mean. Okay. And so what is in here? These are all data items listed on the x-axis. Okay. If this is the mean within 1 standard deviation, so this right here, say the mean, you know how we got the mean is 82.7 on the previous problem? 1 standard deviation away would be that 82.7 plus 10.1, 82.7 minus 10.1. 68% of all of our data items, about 68%, lie within 1 standard deviation. Within 2 standard deviations, all of this right here, that's about 95%. Within 3 standard deviations of the mean, all of this, that's about 99.7%. Okay? So that may seem a little confusing right now, but that is a very important concept to understand. You know, what did we figure out earlier using the standard deviation? The maximum and minimum usual values. And how did we get that? We said the mean plus 2 standard deviations and the mean minus 2 standard deviations. So that means we were actually figuring out the smallest and the largest numbers of usual values. So we usually, in statistics, we consider the usual values to be the ones that would contain 95% of all of the data items. So 95% of the data items are usual. If you have something that's greater than that maximum value or smaller than that minimum value, though, then that's unusual. All right. That's something called the coefficient of variation. And we use this sometimes when comparing different data sets. So what you'll have to do for some problems is you'll have to figure out the coefficient of variation for different data sets. So you have to go through and find the standard deviation of one data set, because to find the coefficient of variation, you have to find the sample standard deviation. Okay? The formula for the coefficient of variation is coefficient of variation, capital CV, equals the sample standard deviation divided by the mean times 100%. Sample standard deviation divided by the mean times 100%. Okay? Look what your book says. In part 1 of this section, we noted that when comparing variation of 2 different sets of data, which I did not go over, the standard deviation should be compared only if the 2 sets use the same scale and units and have approximately the same mean. Well, what do you do if you take 2 different data sets and they don't have close to the same mean? Well, if the means are substantially different, or if the samples use different scales or measurement units, we can use the coefficient of variation defined as follows. All right, so we have the sample mean for that particular set of data divided by, the sample variation divided by the sample mean times 100%. So it's kind of like, I don't want to say it normalizes it, but it puts it in a way that you can compare different sets. The round off rule, round the coefficient of variation to 1 decimal place. Okay, because it's a percent. Let's see if we can do the coefficient of variation for that same data set, that set of Manatee. All right, I know we can. So for that same problem, I think it's problem 10 in that section, we have the sample standard deviation was 10.1. The sample mean was 82.7. We'll say that times 100 to give us a percent. All right, and so I got, if I round this to one place, 12.2%. And that's the ratio of the standard deviation to the mean times 100%. All right, your book goes through and does the same thing with the good old chocolate chips. All right, now, if you recall when we were going over the standard deviation, one of the properties was that it was a biased estimator of the population standard deviation. Okay, this means that the values of the sample standard deviation do not target the value of the population standard deviation. All right, they can overestimate or underestimate the actual population standard deviation. However, the sample variances are an unbiased estimator of the population variances. So that means that sample variances are really close or can predict the population variance. We go over that more in chapter 6. Now, using technology for this section and for this test is fine with me. I would highly suggest that you work some of these out longhand just so that you understand how to do them, because we're not, you know, maybe you need this value and you're not always going to have a calculator. No, that's a lie, you will, but you won't always have one that'll work it out for you. So it really depends on the calculators that you use. I do know for a fact that the TI 82, 83, 84, whatever, the TI series will work these problems out. It'll work them out pretty quick. Just to give you an example, I'll load the TI software here. If you have a TI calculator, this is an 84 plus C. Of course, it's basically the same for all of the versions of the TI, except if you start getting into the ones that do the CAST, computer-aided software stuff, then those are the Inspire calculators, and they're usually a little more complicated to deal with than what we would need. But these calculators, you know, if you go into, if you push Stat and then Edit, what that does is that brings up places where you can put lists of numbers in. So let's type in a list of those same numbers we've been dealing with. Let's say I want to type in my data items. 78, 81, 95, 73, 69, 79, 92, 73, 90, and 97. Alright, so there's my 10 data items in a list. Notice it's in list L1. Okay, that's important. You can see L1 down here on the calculator. If you push second and 1, that gives you L1. Okay, so there's the list. I'm just going to now get out of what I'm in, or I'm going to push the Stat button again. Then I'll push the right arrow to go over Calc, and that stands for Calculate. One variable statistics, so you just hit Enter, the list, L1, Calculate. I don't think you have to go through that same step twice on the TI-83s, but you do on this. You can see, here's the mean. There's the sum of x that we used in our formula. There's the sum of x squared we used in our formula. There is the sample standard deviation, 10.1 to the 1 decimal place, 10.1. There is the population standard deviation, minimum value. It even gives you some other things we haven't went into yet. The quartile, first quartile, the median, and that's also the second quartile, the third quartile, maximum. So you can get all kind of stuff. And you can get it fairly quick with the TI calculators.